Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electromagnetic theory, and we'll take our discussion forward related to basic properties of electromagnetic waves. Okay, so in the previous video we discussed some basic properties, starting with the generation of electromagnetic waves, how oscillating charges and variable currents they create electromagnetic waves, and how Faraday's law and Ampere-Maxwell law equations come into play. Then the transverse nature of electromagnetic waves, which states that the electric and magnetic components, the oscillations, they are in mutually perpendicular planes, which is also perpendicular to the direction of propagation of the electromagnetic wave. Okay, and then we discussed about both the electric and magnetic vibrations, the equations. Both of them, they are in the same phase. There is no phase lag or phase lead, there is no phase difference, and they attain their maximum and minimum values at the same time. And then we discussed about the speed of electromagnetic waves, which is equal to 3 × 10⁸ meter per second, which is equal to 1 by root over mu 0 epsilon 0, and the amplitude ratio of electromagnetic waves, which is also equal to the same value, numerical value, 3 × 10⁸ E0 by B0, this ratio, which is equal to 3 × 10⁸. So now we'll take our discussion forward and we'll discuss some more properties, starting with the average energy density of electromagnetic waves. So before discussing it, first we must know what is energy density. So as we all know, electromagnetic waves, they carry some energy with them. Okay, and that energy is shared equally among the electric and magnetic fields, their vibrations, their oscillations. So that energy, the total energy of the electromagnetic wave, is shared equally. So as they propagate in space along a particular direction, mutually perpendicular direction, they carry that electromagnetic energy. So energy density is, if we consider an imaginary volume, three-dimensional volume, if we imagine, so the energy contained in that particular volume, per unit volume, that is called as energy density, energy by volume. Okay, energy per unit volume of the three-dimensional space, that is called as energy density. Now, average energy density, which is carried by the electromagnetic waves, which is shared equally among the electric and magnetic fields, that is given by, for the electric field, the electric component, that is given by 1 by 2 epsilon 0 E square, where E is the electric field intensity, time varying electric field. Epsilon 0 is the absolute permittivity, 8.854 × 10⁻⁻12 at per meter, and small ue is the average energy density of the electric field. For the magnetic field, it is expressed as small ub, which is the average energy density of the magnetic component of the magnetic field, which is given by 1 by 2 b square by mu 0, where b is the time varying magnetic field. Okay, this one which we have already discussed, this is b, this is e, and mu 0 is the absolute permeability, which is 4 pi × 10⁻⁻7. So this is the average energy density of the electric field, the electric component of the electromagnetic wave, and this is the average energy density of the magnetic field or the magnetic component. Okay, the electric component and the magnetic component. So this is the average energy density. So the total energy density, that is given by ut is equal to ue plus ub, which is equal to 1 by 2 epsilon 0 e square plus 1 by 2 b square by mu 0. this. So this is the energy carried by the electromagnetic waves, which is expressed in terms of the average energy density and is shared equally between the electric and magnetic fields. Next is the intensity of electromagnetic waves. Okay, so the intensity of an electromagnetic wave can be visualized, this whole thing, by imagining a surface, okay, a surface which is held perpendicular to the direction of propagation of the wave. That is, the surface plane and the direction of propagation, it is perpendicular to that surface, the plane of that surface. So if we imagine this surface, then the energy crossing per unit area of the surface, okay, per second, okay, the energy crossing, the electromagnetic energy crossing per unit area of the surface per second, that is energy by area per the energy passing per second divided by the surface area of the imaginary surface. That is the intensity of electromagnetic waves. Basic definition: the electromagnetic energy crossing per unit area per second of the surface which is perpendicular to the direction of propagation of the electromagnetic wave. So here the direction of propagation is along x-axis, so the surface will be in the yz plane. It will be parallel to the yz plane here, this surface, imaginary surface. So energy crossing per unit area per second in the surface which is held parallel to the yz plane, which is perpendicular to the direction of propagation of the electromagnetic wave along the x-axis. So this is expressed as the average energy density, which we discussed here, the total average energy density multiplied with the speed of the electromagnetic wave in free space, assuming that we are considering free space, that is c. If it is held in any particular medium, then the speed of the electromagnetic wave in that particular medium is considered. Okay, so intensity is equal to average energy density into speed of electromagnetic wave in free space, which is equal to c. Okay, so for electric field, it will be, for the electrical field component, the intensity in that it will be equal to I subscript E, which is equal to 1 by 2 epsilon 0 E square into C, because UE is equal to this much, 1 by 2 epsilon 0 E square. And for the magnetic field, the intensity is equal to I subscript B, which is equal to 1 by 2 B square by mu 0 into C, because UB, that is equal to 1 by 2 B square by mu 0. Okay, so the basic thing is that intensity is simply average energy density multiplied with the speed of the electromagnetic wave. For free space, this is the expression, because speed of the electromagnetic wave in free space is equal to c, which is equal to 3 into 10 to the power 8 meter per second. Okay, so we have discussed average energy density and intensity of electromagnetic waves. Then is momentum of electromagnetic waves. Okay, so the electromagnetic waves, they carry energy with them. We have discussed average energy density, we discussed, then the intensity that we have discussed. So as it moves in a particular direction, it transports linear momentum along with it as it travels in a particular direction. So for an electromagnetic wave of total energy, capital U, not energy density, here it is total energy, capital U, and it is moving with a speed c in free space, that is 3 into 10 to the power 8 meter per second. The linear momentum, small p, it is expressed as P momentum is equal to total energy carried by the electromagnetic wave by speed of the electromagnetic wave c in free space. So P is equal to U by C, or linear momentum of electromagnetic waves is equal to total energy by speed of electromagnetic wave. Okay, so this here momentum, linear momentum, that is equal to total energy by speed of the electromagnetic wave. Okay, this is the linear momentum of electromagnetic waves. Next is pressure exerted by the electromagnetic waves. So far we have discussed the energy, intensity and momentum of electromagnetic waves. So it is obvious that whenever an electromagnetic wave strikes a particular surface or it falls on a particular surface, solid surface, it will exert some pressure on it. Okay, because it has both energy, momentum, everything, so it is obvious that it will exert some pressure on that surface. So if we have an electromagnetic wave of intensity capital I moving with a speed c, the pressure exerted by that electromagnetic wave on a solid surface in its path, that is in the direction of propagation, that is equal to the ratio of intensity and speed. Okay, the pressure exerted by the electromagnetic wave is equal to intensity by speed. Okay, this. So the pressure exerted by electromagnetic waves is the ratio of the intensity of the electromagnetic wave and the speed of the electromagnetic wave in free space, because in free space the speed of electromagnetic wave is equal to 3 into 10 to the power 8 meter per second, which is equal to c. For any other medium it will be that particular velocity v, which will be always less than c. So these are some of the properties of electromagnetic waves. We discussed some in the previous video, and in this video we discussed the energy density, the average energy density of electromagnetic waves for both electric and magnetic fields, and the total energy density, then the intensity of electromagnetic waves, and then the linear momentum and pressure exerted by electromagnetic waves. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.